So I'm Linley Gwennap still, and going to give a talk for the next 45 minutes or so on segmenting the IoT processor market. So wanted to dive a little bit deeper into some of the technologies and some of the products in the IoT market, and then we'll have some time to talk about those, have some questions and answers after I'm finished. So for those of you that don't know me, I am the founder and principal analyst at the Linley Group, and also editor-in-chief of Microprocessor Report. So hopefully you've had a chance to take a look at Microprocessor Report on the table outside, and been analyzing the semiconductor market for about 20 years now, and started off doing CPU design way back in the old days. Oops, sorry. So in terms of the presentation and kind of how we break down the market, I want to talk about processors for Wi-Fi, and then look at 802.15.4, LTE, and then spend a little bit of time on wearables at the end. So when we're looking at the IoT processors, first of all, in terms of the way we write about the market, we're trying to focus on processors that have integrated wireless connectivity. Now, I know a lot of IoT devices don't necessarily use a processor with integrated connectivity, but we cover application processors and microcontrollers separately. So what I'm going to talk about this afternoon is this sort of emerging category of processors that are really designed for IoT devices, and a key optimization that we see there is this integrated connectivity. So these can be either microcontrollers that have integrated connectivity, or they can be kind of an application processor with integrated connectivity as well. So, but not necessarily just a standalone processor. As I said, we would cover those elsewhere. And these products typically integrate the RF transceiver, they integrate the RF front end, so that you've got the complete, pretty much a complete radio subsystem, and the processor with enough memory to run an IP protocol stack, since these devices are often connected directly to the internet. So, as I said, I'll start off with Wi-Fi. Just a little bit of discussion on Wi-Fi to start with. One of the reasons that Wi-Fi is popular for IoT devices is because most broadband homes already have a Wi-Fi router there, so that if someone buys an IoT device with Wi-Fi, they take it home, they connect it to their existing network, there's no extra cost of creating a new network in their home. But Wi-Fi is not necessarily ideal for these devices because it's really designed for PCs and other high data rate devices that are moving large amounts of data back and forth. So we've spent a lot of time over the past several years coming up with faster and faster versions of Wi-Fi, but now we have these IoT devices that really don't need that capability. I mean, when you look at most Wi-Fi devices today, the minimum data rate, the slowest they can possibly run, is 7 megabits per second. So, which is far more than most of these IoT devices need. And then because your Wi-Fi device is designed for these higher data rates, it uses more power than things like Bluetooth or Zigbee, and they also cost more because you build in a lot of capability into these into the chips. Now there is a new standard called 802.11ah, which is being branded as Halo by the Wi-Fi Alliance, and it's designed to really optimize Wi-Fi more for the IoT space. So it does several things. The main one is to reduce the channel width from 20 megahertz down to 2. So now you've only got 1/10 as much RF bandwidth to deal with, and that greatly reduces the data rate that you can pull out of the narrower channel, and then that saves power because you're not processing so much data, and it saves die area because you're not processing so much data. It makes the RF subsystem simpler, which also makes the die area smaller. So there's a lot of benefit here. It also, the standard adds mesh capability, so that now in a typical Wi-Fi network, everything has to talk to the access point. But now in these Halo systems, you can talk to another device that talks to another device that eventually gets you back to the access point, and that can increase the effective range by allowing you to create these meshes. And then as another range enhancement, Halo is designed with an optional 900 megahertz band, and you can get better penetration through walls at the lower frequency, and that can increase your effective range as well. So a lot of good ideas here embedded in this new standard. The standard was released at the end of last year. We expect to see products shipping this year, implementing this new version of Wi-Fi. Now, the problem is going to be still, if you're using this Halo standard, I mean, you need a gateway and access point that supports it, or else it doesn't do you any good. So I think it's going to take time for the access points to implement this, and then the devices as well. But I think there's some good prospects for this new standard moving forward. Now, if we look at the existing products now, of course, none of these products implement 11AH, and in fact, most of them don't even implement 11AC, which is popular in most of the access points today. So the IoT Wi-Fi chips tend to focus on the 11N standard, the older standard, to kind of simplify the design, and they don't really need all that extra speed upgrade from 11AC. And in fact, these devices also typically work only in the 2.4 gigahertz band. 11AC really requires the 5 gigahertz band to achieve any faster speeds. So by focusing on 11N and by focusing on 2.4 gigahertz, I mean, that's kind of as cheap as you can get before this new 11AH standard comes out. And we do see a few companies like MediaTek and Qualcomm that are supporting the 5 gigahertz band as well. And there are some benefits of the 5 gigahertz band, even if you're not running 11AC, because there's fewer devices there. The channels are clearer, so you can potentially connect better or get better range. But for most IoT devices, 2.4 gigahertz is sufficient. And these are pretty low-cost processors, so they're targeting IoT devices like sensors, smart lighting, appliances, and so they want to keep the cost pretty small. So these are some of the products that we reviewed. There's a Marvell chip here, MediaTek, Qualcomm, Realtek, TI. In fact, this is the TI Simple Link part that was mentioned yesterday. Most of these are built in 40 nanometers so that they can take advantage of the 40 nanometer RF CMOS technology. They are integrating the RF front end, so having an RF friendly process is useful. So they tend not to want to push down into the newer nodes or the FinFET nodes, but they stay back in something like 40 nanometer or even older technology in some cases. These are all based on Cortex M4 with the DSP extensions, so that you can do some sensor processing using the DSP extensions. And then these are all designed to plug into a Wi-Fi network, so they can have their own IP address. They have to run an IP stack. These chips actually integrate the SRAM so that they can run the IP protocol without any external DRAM. So these chips are designed, to reduce the BOM cost, minimize the cost to the end user for a very simple IP-enabled Wi-Fi device. Now, the MediaTek and Qualcomm chips, as I mentioned, support 5 gigahertz band. They also support some other modes, including Bluetooth, and in Qualcomm's case, 802.15.4. So if you are designing a system where you need some of these extra capabilities, maybe you want to be able to use a Bluetooth connection from your phone to configure the device and then allow it to communicate using Wi-Fi, or maybe you want the device to act as a hub and connect to other 802.15.4 devices. You have the option with these more sophisticated chips to do those things. But some of the other vendors are just focusing on the basics. Now, if you do want to run a more sophisticated application on your Wi-Fi IoT device, then there's a product available from Cypress, which used to be available from Broadcom. So this offers a higher performance Cortex-R, Cortex-R4 CPU running at 320 megahertz. So now you've got enough CPU power to do some more interesting things. This product is commonly used in wireless speakers, so that you can stream audio to it. It can do room-to-room synchronization, so that so it's got the faster CPU in there to do that. But then now you have to have external DRAM. The chip has a DRAM controller, but now you have the cost of the external DRAM. This chip is going to be used in more expensive devices that need this extra kind of performance. So then there's a group of devices that are focused more on even lower costs, and so for really minimizing cost and power, using some version or some way to go than trying to wrestle with Wi-Fi. So this is a standard that's been around for quite a while. It defines layer 1 and layer 2 for very low power, low data rate kind of networks. And so when we're talking about low data rates, we're talking in the kilobits per second kind of data rate. What has happened now is that different companies and different groups have grabbed on this IEEE standard and built things on top of that. So this IEEE standard is the basis for Zigbee. It's the basis for Thread and some of these other protocols, and as well as various proprietary protocols that companies have built on top of the basic 802.15.4. So, and then you can really use this in different frequencies as well. It's typically used in unlicensed, the 2.4 gigahertz band. It can also be used in sub-gigahertz, various bands there, particularly for these proprietary protocols. They may go sub-gigahertz. Then when you're building these protocols on top of 802.15.4, I mean, now you can add higher level capabilities. So for example, Zigbee supports a mesh capability where you can communicate from device to device. Zigbee Pro adds security features on top of the basic protocol. And then, whereas the 802.15.4 itself is not an IP protocol, these other protocols like Thread have built IP addressing on top of the base layer. So if you want to have a device with an IP address and connect and run an IP stack, you can use something like Thread, or Zigbee has a version as well, and implement the IP addressing that way. So these protocols are good for, again, very low-cost IoT devices, remote sensors, smart lighting, smoke detectors, things like that. It's often used in some industrial applications again, to connect remote sensors. Because in a home, you wouldn't typically have access point or a gateway that directly communicates to these devices, you'd probably have some sort of hub that then bridges everything over to Wi-Fi. So the picture here is a security system or smart home system that you could buy online. It comes with a number of different kinds of devices, smoke detectors, cameras, different things that all communicate via Zigbee, and then it has this hub device that aggregates all the Zigbee signals together and then communicates via Wi-Fi up into the gateway, your home access point. And then because of this hub configuration, each individual Zigbee device doesn't need to have its own IP address. It doesn't need to run an IP stack. So the Zigbee devices can be very simple, and the hub has to be a little bit more more complicated to convert over to Wi-Fi, and then it's only the hub device that has to have an IP address via the Wi-Fi. So these are some products that we're covering that can support these various versions of 802.15.4. You'll notice these all use very low power Cortex M0 or M0 Plus CPUs. So to minimize cost, these are microcontroller cores running at around 48 megahertz, and and then they integrate the SRAM and the flash that's required to execute these very simple types of algorithms and programs in these low-cost devices. And really the differentiation between these types of products is in some of the IOs, whether you need analog IOs, digital IOs, if you need a keypad, a touch interface, and they may differentiate on the amount of memory in case you need more memory or less memory to run your algorithm. So these are pretty generic chips and really designed for low cost. Now there's some of these chips, and I mentioned earlier, that support multiple protocols, and so companies like Silicon Labs and NXP offer these multi-mode chips where that are good for something like the hub in that previous picture I had. So you could you could communicate via Bluetooth, you can communicate via 802.15.4, whatever flavor you need. But a lot of times what these products do is they switch back and forth. So you can't necessarily use both protocols at the same time. So so they kind of time slice and check the do I hear any Bluetooth beacons? Anybody asking for Bluetooth data? Now switch back and check the Zigbee network and see if anything's going on there. So as an example, a smart light bulb from Philips. It generally uses Zigbee to control the lighting, but if you want to go in with a phone, you can connect via Bluetooth, low energy, and configure it that way. So, and then for some of these multi-mode chips, they'll upgrade from Cortex M0 to Cortex M4, so that now you can maybe have a small user interface via Bluetooth, or you can connect via Wi-Fi, so you need a little bit more performance to do that. Sorry. There we go. Then moving on, we're looking at IoT chips that connect to LTE. Now, the advantage for LTE is that you can cover a broad range of area with a cellular connection. And so LTE is ideal for mobile devices, that is anything that moves around, cars or other equipment, and any kind of asset that you might want to track that moves around, a shipping container, forklift, anything like that. So, if it's going to move out of range of your, Wi-Fi base station, for example, then you're out of luck. So, using LTE, solves that problem. It also eliminates some hassle that companies are seeing where, they may put a Wi-Fi interface, say on a washing machine and ask the customer to hook it up to their Wi-Fi network, but the customer takes the washing machine home and says, I don't really need the internet capabilities, so I'm just going to wash my clothes, and then they never connect it up. The appliance makers would like to get data back from that washing machine. They'd like to know how it's being used. Maybe they want to be able to upgrade the firmware. Maybe they want to do predictive maintenance, but the customer doesn't enable the function. So if you put a cellular interface in that washing machine instead, then wherever that washing machine gets installed, it just connects up to the cellular network, and the appliance manufacturer can talk to their washing machine. So so that is attractive for certain use cases where the customer may not be, the end user may not be motivated to connect it up, or certainly for situations where there may not be a Wi-Fi connection. Now, the downside of LTE is that you typically have some kind of data fees. So if I'm going to put a device on a cellular network, the operator is typically going to charge something. Now, those rates have been going down. Verizon advertises, I think, a $1 a month rate for these IoT devices, but if you negotiate with Verizon in bulk, you can push that down to 20, 30 cents a month, or even lower in some cases, but it still adds up. I mean, if you think, a few dollars a year, your device is going to be in the field for 10 years, I mean, that's still $20 or $30. That's a lot, more than you're paying for the module itself to connect to the cellular network. So, if you can connect to a Wi-Fi network and you don't have to pay data rates, that's a great deal, but there's definitely some use cases where cellular makes sense. And in those use cases, we're seeing a lot of interest in these new LTE modes. Again, just like the Halo standard, what the cellular guys have been doing is trying to take LTE, which is designed for super high data rates, and then crank it down and try to optimize it better for IoT. And so first they came up with what's called Category M1, which is designed for 1 megabit per second rather than hundreds of megabits per second, which is still good enough for voice. It's still good enough to exchange data at some reasonable rate. And then Cat NB1 and Cat NB2 go even lower, down to 250 kilobits per second or below. And so now you're really minimizing the cost and the power to implement an LTE connection. And then the next generation is going to be 5G or 5G NB. So that will simplify the protocol even more, because right now we're just kind of using the same LTE protocol, but 5G will actually simplify the protocol, add some mesh capability, and further improve the applicability of cellular to these IoT devices. Available for IoT cellular, implement either Cat M1 or the NB standards, and there's kind of two ways to go. What Qualcomm has done is pretty much just taken their existing LTE modem, which has a Cortex A7 in it, and then just kind of requalified it to support these lower speed standards. So if you need the application level performance, if you want to run Linux on this processor, and run some kind of user interface, Qualcomm's solution has the CPU capability to do that. But what Sequans and MediaTek have done is focused more on reducing cost and using Cortex-M core instead of Cortex-A7. They've integrated memory, which Qualcomm doesn't have, and also integrated the RF transceiver and the RF filters, which Qualcomm hasn't done. So if you use the MediaTek or Sequans, I mean, you're really reducing the bill of materials, you're reducing the cost, and you get almost everything you need in a single chip. So in fact, the Sequans Monarch SX chip even integrates a GPU, an audio engine, a display controller, so you can build small devices with a small display, like maybe a thermostat or something that would be on the wall to control other devices. So they packed a lot of stuff in there, and still trying to keep the cost down. MediaTek is taken more of a bare bones approach. They focus exclusively on the lower data rate of category NB, and so they don't integrate some of these other graphics and display features. But if you just want, say, a mobile asset tracker, the MediaTek chip has pretty much everything you need, other than the GPS to build that kind of an asset tracker. So you've got some different solutions here that are optimized for different cost points, different end applications, and we expect to see more companies jumping into this market, particularly now that the operators are starting to support the Cat-M and Cat-NB. And then moving into the wearables, there's several segments in the wearables market, and you can put different names on them, categorize them in different ways. But we would look at sort of an entry-level device being these very cheap fitness trackers that don't do much of anything other than count your steps, and so they tend to focus on the lowest possible cost. And then you kind of move up into a higher-end tracker or basic smartwatch, where now you might have some new features like GPS capability, and so they're trying to differentiate more on what kind of features do you get and what's your battery life. And then as you move further up, you get into kind of the Android-based or iOS-based smartwatches, where now you need a more sophisticated processor, Bluetooth, GPS, more memory, and then you start driving up the cost of the watch. And then you get into the very high end, which would be something like the Microsoft HoloLens that I'm showing here, where you have to have a very sophisticated processor and display capability. So if you start it with the entry level, again, really these are focused on low cost, and so the example here is an NXP microcontroller with an integrated Bluetooth radio, and they've focused on Cortex-M0 as the CPU. Again, probably the lowest cost CPU you can get, and integrated the memory, integrated both flash and RAM, integrated the RF front end. So again, everything is kind of in here to keep the system cost as small as possible. There's several other companies, Dialog, Microchip, ST, that offer similar products in this category and support these entry-level wearables. Then if you want to add some more features to your wearable, you may want to have like a Cortex-M4 CPU with DSP extensions, and now you can run more application-type software. Maybe you have a GPS in here, maybe you have more sensors, you want to aggregate some of the sensor data, you can do that with a faster application processor. This chip is a Cypress microcontroller. It actually has a second CPU, which is a Cortex-M0 that supports the Bluetooth subsystem, and it also integrates a security block to help implement security, which, as we're going to talk about in the next session, is a very important function in these wearables. And And then I also mentioned here a MediaTek part, which is similar to this one, but it adds a DSP core, so now you can do more audio processing, even maybe have a simple display. So if you have a low-cost smartwatch, you'd have a very simple display, small display with a user interface, so this kind of chip would be good for that. So, so depending on what kind of features you're going to add, you've got some different design options out there. And then as you get into these smartwatches that are running some kind of high-level operating system, now you need a more sophisticated CPU, which typically would be like a Cortex A7. So the processors I've shown here, a lot of these are kind of, the company took their smartphone chip and kind of stripped it down a little bit to squeeze it into a watch environment. So you've got some pretty powerful processors running at a gigahertz or faster, and in some cases dual cores even. You got some kind of for a smartphone would be a pretty basic GPU, but it's certainly more than enough to run a user interface on a watch size display. But then you have to add external DRAM, you have to add external flash, and then you have typically some kind of connectivity baseband built into these chips. But you need to add external RF in many cases as well. So now you're going from a highly integrated device to a processor that needs a lot of extra chips around it, and that's why these watches tend to be fairly expensive, and the battery life on a lot of these smartwatches is not very good, because basically got a smartphone on my wrist. So these are good for those kind of products, but if you want to reduce the power, you're probably going to be looking at some of the lower end products. So we took a quick tour through a lot of the different processors that are available with integrated RF for the IoT space. We saw the Wi-Fi processors are really great because they connect directly to the home router, and that makes it easy to install in most homes. But if you really want to minimize power and cost, you're probably going to look at these 802.15.4 type MCUs. But then you probably need some kind of hub or bridge to connect them to your Wi-Fi. So we see these Zigbee type devices being good. If you buy a bunch of devices from one vendor, like let's say you buy a bunch of smoke detectors, you probably buy a number of smoke detectors at the same time from a single vendor. You install them in your house, or the builder installs them in the house, and then they put in that hub to connect everything to Wi-Fi. So that's a good approach, a good time that you might want to use something like Zigbee instead of Wi-Fi. And now if you have an application device that moves around and you need to keep track of it, outside of your house or outside of a factory, that's where cellular is a great solution. And it also eliminates the need for the end user to have to configure or attach a cellular device to the network. It comes pre-installed. So the downside of cellular is that is the monthly data fee. But we are seeing these NB-IoT processors that the cost is coming down, and even though they're still more expensive than a Wi-Fi chip today, as we heard yesterday, the cost is approaching parity with Wi-Fi in terms of the chip itself. And in terms of the vendors, we see the microcontroller vendors really having the advantage in most of these markets because they're used to selling at these low price points. So for Wi-Fi, for Zigbee and those kind of products, even low-cost wearables, the microcontroller vendors have a broad range of products, and they're doing very well, whereas companies like Intel are withdrawing from that microcontroller segment of the IoT. But where we see some of the smartphone processor vendors and other processor vendors having some traction is in the LTE market, because obviously they have the LTE capability. And even in the high-end wearables, something like an Android watch is very similar functionally to a smartphone. So the smartphone companies like Qualcomm and MediaTek are doing well in those kind of devices. So, there's still a lot of change going on in the IoT market. We see new end products emerging all the time, and then new processors and new processor vendors even coming into this IoT market as it grows and becomes more robust. So a quick commercial. If you want more details on all this, we have a guide to processors for IoT and wearables where a lot of this data came from. You can see a copy of it outside. So if you're interested in really getting into the nitty-gritty on these products, please check it out.